Look at section 1.1, which deals with nets and drawings in geometry. If you're not spatially gifted, which I'm not, most of us are not, some of this can be very difficult for you because you got to visualize a 3D picture on a 2D page. So I have developed over years accommodations to deal with stuff like this because my eyes don't see the way normal people's eyes do. So I have no issues with you cheating with an appropriate accommodation. You'll see what I mean in a minute. So we're going to look at some vocabulary. So I want you to identify whether these are two-dimensional or three-dimensional figures. You might want to use a pencil or an erasable pen in case you make a mistake. You can use 2-D or 3-D to represent, so you don't have to write it all the way out. So what's this picture showing? Two-dimensional or three-dimensional? 3D. So this is 3D. So when you look at a three-dimensional picture, it's 3 dimensions because you can see it. So one of your dimensions is you can see it. The second dimension is, if I'm looking at an object that I can actually see, so here's a sugar cube, that's also three-dimensional. I can see it, can't I touch it? So that's my second dimension, touch. What's my third dimension on a 3D? What makes this sugar cube different than just the top of my desk? Volume. Volume means that I can pick it up. It has a length, a width, and a height to it, for lack of a better word, since this is a cube. But I can pick it up. That gives it volume. And you might want to put volume in. So those are your 3 dimensions. Something that's 2-dimensional, like number 2, this is 2D, I can see it and I can touch it, but I cannot pick it up. So your 2-dimensional means you can see it and you can touch it. So like the wall in this classroom, if you just looked at don't consider that the wall has volume. I can see that wall and touch it, but I can't pick the wall up. If I were Hercules and I gave it some depth, some height, and some width, and I were Hercules, then I could pick it up. So technically my wall is 3D, but you're going to have to look at certain things when they give you a real life situation. Everything in our life is 3-dimensional. We live in a 3D world. So technically everything is 3D. So you don't get too technical when they're asking you questions in this particular section. So what's number 3? 3D. So that's not so bad. Then we're going to look at a polygon. They give you the definition here. A polygon is a 2-dimensional figure, so you can only see it and touch it, with 3 or more sides. So if I were you, I'd be using my highlighter. The important part of the definition is it's a 2-dimensional figure, and it's got 3 or more sides. So you cannot have a polygon with 2 sides, where each side meets exactly 2 other sides at their endpoints. So here's an example of what a polygon looks like. In short, and this is what the main idea is telling you, a polygon is a closed figure, and you will hear me saying that often. It is a closed figure. And what they don't say in here that I want you to add is a closed figure with straight edges. Hi. Just find any seat, and you and I will chat. If you will pick up on the far left tile there, do you see something that looks like this? Yeah. Pick that up. Yeah, just sit in that empty seat. There you go, Mara. Yep. All right, so technically, a polygon is a closed figure with straight edges. Nowhere in any of this, the definition of the main idea didn't mention that it had straight sides. So if you had something that looked like a ice cream cone, technically, that's two-dimensional. Does it have 3 or more sides? There's one side, there's one side. Think of this as a wall, that could be a side. And some of you would be thinking, oh, that curve is another side. Well, a side has to be straight, and that's what they haven't clearly stated to you here. This is a closed figure, and no sides cross each other. Oh, let's underline that. Got a highlighter. No sides cross each other. None of that occurs in that ice cream cone shape. But the fact is, you cannot have curved edges. So put an X through this. It is not a polygon. So if you think about the track out at the football field, the track has 2 straight edges and then a curve on either side. It's not a polygon. What about the football field itself? Yes, that is a polygon. The track around it, not a polygon. All right, so here I want you to underline what you think belongs there. So in other words, on number 4, a polygon is formed by, is it 2 or 3? Okay. So underline your 3 or more, because that's technically what goes with it. 3 or more straight sides. And then go ahead and fill in the rest, 5 through 11. What you think they are, based upon our conversation. All right, share your answers with somebody around you, 1 or 2 people around you that are next to you. In front of you, behind you, beside of you. Oh, look, our clock is sort of coming back. Look at how time flies when you're having fun. All right, so let's stop. Let's see what you said. Number 5, a circle is or is not a polygon? It's not as correct. Why? It doesn't really have any sides, right? It's just one big curve. So because a polygon has to have straight edges, it's not. What about number 6? A triangle or a rectangle is a polygon with 3 sides. Triangle. Try, and you'll learn all of the names of polygons if you didn't in middle school. Try means 3. Oops, I suppose I just let that one go. But you knew that, right? Sides of a polygon are straight. No curved sides in a polygon. Number 8, is it 2 or 3 sides of a polygon meet at the same point? It is 2 because that means that it looks like this. The minute I have a 3rd side that meets at a point, I now have what kind of a figure? A 3-dimensional figure. So that's why it's 2. And so that one you might have missed. We haven't discussed that. And then 9, 10, or 11, which are not polygons?
9, 10, 11.
So we got all of them? 9 is not a polygon, and I highlighted why. There's a gap there. It is not a closed figure. So you might want to write in there, not closed. Because oftentimes I'll ask you why. Why is it not? So the reason for that is not a closed figure. One of the big things about this class is you got to be good at explaining why. So number 10, correct, is not a polygon. And here's why. It has straight edges. It's a closed figure, but look at how side MP and side NQ cross each other. And remember up here, no sides can cross each other. So you might want to write here, no sides can cross each other. What about 11? Is it a polygon?
Yes.
Does it have straight edges? Is it closed? Two-dimensional? Any curves? Any sides that cross? So it meets it totally meets the definition of polygon. So it is a polygon. Was there anything in there that made you think it wasn't? Okay. All right, so let's look at the second page. So now we're going to look at what a net is. All a net does, think of your cereal box, if you actually had cereal this morning, or a graham cracker box, or whatever comes in a box that you need. Couldn't you cut that box apart without, you could cut that box apart and keep it in one piece, couldn't you? If you did it carefully. That's a net. And if you do it correctly, that box will fold back to give you the correct figure again. So here's a little cube right here. So you'll agree that this is a cube. And I don't have any sides that are overlapping, right? Doesn't appear. I'm trying my best to keep it closed. And if I open this up, this is just one net for this particular cube right here. And I happen to make this one here. And the reason why I made this is because I cannot visualize 3D on 2D paper. I have different eyes than the rest of you. I had surgery when I was really, really little. I won't go into the whole long story, but I physically can't. So if you need to answer some of these questions, if I were you, on your homework tonight, I'd make off of your graph paper a little net for whatever it is that they're looking at, and feel free to print it out and use it as your cheat sheet. This is a viable cheat sheet. Now some of you will be able to look at this because this part's going to be hard for some of you. And you'll just be able to get it and visualize it immediately. So I made the net so that those of you who don't see it on paper, I can show it to you when I put the net together. All right, so a net is a two-dimensional or a three-dimensional diagram. It's two-dimensional, right? Because it's flat. You can see it and touch it. Okay, technically I can pick it up, but we're not going to get that technical. It's flat, right? So underline, two-dimensional, or circle. I don't care if you circle or underline. That you can fold to form a what figure? Now when I fold it, what kind of figure do I have? Yeah, it's 3D. So circle the net that you cannot fold into a cube. So out of these three, and slow think about that. If you fold it, you're looking for places where it would overlap. Leave an open end. Because when you take that flat net and fold it, you want it to be a closed three-dimensional figure. It should not be an open box. No overlapping flaps. What about this one? Wouldn't all of these wrap around each other? This side would meet with that side, so it'd wrap around each other and leave two open ends here and here, right? So these are going to wrap around each other like this, and you'd have an open end here and an open end here. Don't those fill the open ends? Would they fold down and fill that? This will make a cube. If you don't believe me, you have to cut it out and fold it to see it. What about this one? These three are going to fold down, right? And these are going to fold down. That's going to fold down. What's going to happen on this one? You going to have anything overlapping? This one's not going to work. If I have time, I'll make it and show it to you. But it's going to overlap where? Yeah, this right here is in the wrong spot. this right here should be either here or here. But this right here is causing the issue. Because when this folds down and that folds down right here, this is going to get squished, crinkled. You'd have to smush it to make it go in there. It's not going to work. What about this one? How is this one similar to this one? What do they have that's the same? This has 4 in a row, right? Does this one have 4 in a row? The only difference is where these two are placed. Does it matter where these two are placed? No, so long as they are opposite of each other. Now, if they're diagonal to each other, that could create an issue. It depends on where they're at. This one is different from this one, and it's different from those two. It does not have 4 in a row, but that's why I made this one so that you could see that it actually did fold as a cube. And now it's going to start asking you some questions. Suppose that you folded it into a cube. They're trying to get you to do it without actually folding it. What number would be opposite each face? So, face number 1. What number is going to be opposite that face and what is parallel to it? Some of you think 6. Well, can 5 be opposite it? No, because it's touching it, right? So what's going to happen is 1 is going to be here and 5 is going to be here, and when it folds, 1's going to be on top and 1 will be on the side or something to that nature. They're going to make an L shape to each other, right? So it can't be 5 and it can't be what? 2. So it's either got to be 3, 4, or 6. Doesn't 4 touch it also? So they're not going to be opposite each other. So it's got to be either 3 or 6. So if you think about it, if I fold this here, the 4 is going to connect to the 5, and then what's the 3 going to end up doing? It's going to loop under, and won't the 3 actually be directly opposite the 5? So the 3 and the 5 are going to be parallel to each other, won't they? So if 3 and 5 are parallel to each other, it can't be parallel to 1. So what does that leave us? So whoever guessed 6, you are correct. So here's 6, and let's just prove it, because some of you still don't see that. So here's my net. I'm going to fold the 3 and the 4 down, and so you can see that there's the 5. My big fingers are in the way, and isn't the 3 directly opposite it, right? And so here's my 1, and there's my 6. So if I fold those, so there's my 6, and then directly opposite it is indeed that 1, isn't it? All right, so what about 3? We already discussed that one, didn't we? 3 is opposite of 5. And what about 4? 2 is a really good guess. Why? 4 is touching 3 and 5, so it can't be opposite those. It's also touching 6. Full edges it's touching. It's also got a corner in common with 1, so it can't touch 1. The only one that's left over is 2. So you can do some logic reasoning without looking at the net, but it takes a little bit of practice. So 4 has to be 2. So then they give you something somewhat of a different view. Now they're giving you what's called a corner view. You can only see 3 out of the 6 sides of that cube, but you still have the net to look at. And they turn the cube too. So for some of you, here comes that spatial reasoning where you've got to like turn and flip and rotate something in your head and try to think about it. So all we can see really is the 1 and the 5. We're trying to guess what this one is. So if you look at the 1 and the 5, here they are touching each other here. What other one is the 5 is directly below the 1, correct? And so we're looking for a cube that's touching both the 5 and the 1. What cube touches both 5 and 1? Does the 3 actually touch 5? No, because it's going to be directly parallel to it, so it won't touch it at all. So the 4 shares a whole side, right? I know that the 4 also shares a side with 1, because anytime I can make an L-shaped connection, like from here to here, won't those two meet? when that net is connected. So that 4 does touch the 1 also. So isn't that the missing side is the 4? So this is 4. And again, if you don't believe me, let's look at it. So here's my cube. Let's just show the 1 and the 5 in the corner view. And so here's your corner view. There's your 1 and your 5. What else is showing? That 4. All right, try that one. This one has been turned quite a bit because it's using the 2 and the 3, which is hard because they're not even touching each other. But think about where they might touch each other. If you look at these 2 nets here, technically, where would the 2 fall into place with these 2 nets? Because we could technically move that 2 and create a different net and still get the same cube. Where would you move this 2 to create a net where you have 4 in a row? Right next to the 5. So, do you see how then it meets up with the 3? So the 2 and the 3 meet up. So the 2 and the 3 touch each other, and something also touches both the 2 and the 3. This is one of the hardest ones to see. What do you think it is? 6, is 6 going to touch the 3? You got an L-shaped thing here, yeah, so 6 touches the 3. Will 6 touch the 2? This is where some of you in 12 is cutting out. So here's my 2 and my 3. And then they have it turned this way. So there's the corner view with 2 and 3. What's popping out there? It's actually the 1. Hard to see, isn't it? So that's where it starts to get tough. Now you're thinking, oh, I can see how I might want to cheat with a net. Go right ahead. All right. Think about that one. That one's a little easier. What do you think it is? It is 3. Think about it this way. The 6 and the 4 touch each other and they've rotated it, right? So here's the 6 and the 4. There's the part where they're touching each other. That's this edge right here. So if you rotate it, the 6 also touches the 3 and the 6 also touches the 5. But we're looking to see what touches both the 6 and the 4. So what touches both the 6 and the 4? Well, the 3 touches both the 6 and the 4, doesn't it? The 5 touches the 4 and the 6, doesn't it? So it could be either 3 or 5, but think about how it's rotated. Remember, 3 and 5 are what to each other? They're parallel to each other, or they're opposite each other, right? And so because of how they've moved it, if the 6 is moved this way, right, then they've taken this net and they've moved it this way, so doesn't that 3 have to be up top and the 5 is on the bottom? And here's where your net is going to show that. So here's my 6 and my 4. The 6 is turned to the left. That makes that 3 up top. So there we go. All right. So the net at the right folds into the cube shown. Which letters will be on the top and the right side of the cube? So they're asking you a question, really not expecting you to answer, but it depends on how you turn that cube. So here we go. 4 of the 5 letters will touch some side of face B, because B has 4 sides. Cross out the letter of the side that will not touch some side of face B. We'll cross out the ones that you know for sure, that you can just see off of the net, are not going to. Well, They want you to do what? Cross out the letter of the side that will not touch. Okay, so I would underline the letters that do touch. What letters do you know just by looking at the net that are obvious that touch B? A and C. So those ones you don't want to cross out. Those definitely touch it. Then think about, look for any L-shaped patterns. Like for instance, from here to here is an L shape. That means that B and E are going to end up touching. And don't they share a corner anyway? All right, so you're going to want to underline E. So you have a choice between D and F. Now you've narrowed it down to 50-50 shot. Here's D and here's F. Which one of those touch B in some way? F, it has a corner touch, plus it also has this L shape that they have in common where those are the sides of the meet. So F is going to touch it. That means that D is not. Which side of the cube will that letter be on? So where's D going to end up being? It's going to be at the top, it's going to be at the bottom, the right, the left, or the back. What's B considered right now? The front. And so if it's not touching, it has to be parallel to it, doesn't it? So that makes it the what? The back. So answer the next two questions based upon what we just did. So what do you think for 18? Which face is to the right of face B? So C is obvious, right? But I'm interested to see how you would answer. How do you know? How are you going to answer that? That's the harder part. How do you know? Don't they share a side? So that's what I would say. C shares a side. And I would say the right side of B. What about 19? Which face is on the top of the cube? E, right? It's got that L-shaped thing. So how are you going to say, how do you know? They do share a side, but it's hard to see off of the net. So I would say that B and E have an L-shaped side that they will share when the net is folded. Okay, so flip that. Answer questions 20 through 22. Actually, answer all the way through 23. Go all the way to 24. Answer all the problem too. So share your answers with those around you. Right or left, see if they agree. Or see if they have something slightly different, if that's okay. All right, so let's talk about this. Let's look up here. Now, some of you might have said false for number 20 because you're looking at a three-dimensional picture on a two-dimensional page. And it is true that three of the faces are rectangles. Now, I'll grant you that those rectangles look like parallelograms, don't they? They're actually rectangles. So there's one of the issues with drawing a three-dimensional figure on a two-dimensional page. A rectangle will nearly always look like a parallelogram. So that is true that three of the faces are rectangles, and when we see the net below, you'll see where they're at. But typically, and you'll learn later that this is called a prism, all prisms have at least some rectangular faces. 4 of the faces are triangles is false. Only 2, the front and the back, are triangles. Only the front and the back. The figure above has 5 faces in all. That is true. It's got the front and the back, which are triangles, and then each of those triangles has 3 sides to them. So that means that you have the 3 rectangles going around the 3 sides of that triangle. That's 3 more sides, giving you 5 total. And if you look at the proper net below, oh, here's the description. So the net has 2 triangles and 3 rectangles that fold to give the figure above. That's all you had to do to describe it. Tell what its shapes are. Shapes of the faces. So faces are flat 2-dimensionals, figures, polygons. Edges are the sides that form those polygons. Vertices are the points where 2 edges meet. So this is the proper net here below, and so you can see that here's the front and the back, and these rectangles are the sides that go around. And so now when you look at the net, you can actually see that yes, those are rectangles. They're not parallelograms. This net here is for a rectangular pyramid because these triangles all come up to a point. It does have 5 faces, but it's the wrong net. And then this one is a triangular pyramid, and it only has 4 faces, not 5, so it can't be the proper net either. Now, what you can see coming from this is finding surface area of these 3-dimensional figures by looking at their nets. I could find the area of this triangle. Granted, you don't know the height. There's ways to find it, but you don't know it. But you can find the area of the triangles, add them together. And you can find the area of each of the rectangles, add those together, and then add all that together to get your total surface area. And so that's where they're kind of going with the nets. All right, let's look at what's called an isometric drawing. So you need to add a definition here. An isometric drawing is essentially this, but this is called isometric dot paper. And so you can get isometric dot paper off of my website. I'll see if I have enough for each of you, but I may only have one piece of paper for you to do your homework with tonight. I'll have to look. But isometric means that it shows a corner view of a 3-dimensional 3D figure. The thing that an isometric drawing does not show is, in this case, you're going to be using cubes. And if you need to get some sugar cubes from me before you leave today in order to see, this is another way to cheat on isometric drawings, because if I ask you how many cubes are in that drawing, how many cubes do you visually see? 3. But how many cubes should be in the figure?
4.
Because if I don't have a 4th cube, won't that top cube fall down? So in order to build this, wouldn't it look like this? There's my corner view, right? And so you have to have that 4th cube there. It's falling apart. So this is the actual 3-dimensional thing that they drew isometrically. So now we're looking at the top of that, right? We'll talk about different views in a minute because that's a different type of drawing. So we're going to put it on this paper. You can see, well, it's hard to see, that they drew one of the edges for you. So you're just going to redraw this on the isometric dot paper. You need a straight edge, so your student ID works well as a straight edge. But before we draw it, let's talk about how many edges you can see. Remember, edges are sides of the polygon, so it's hard to count. Try to think of this in terms of levels. So on the top level, don't I have 1, 2, 3, 4? Then go down to this level here, I've got 5, 6, 7. Go to the tops here, I didn't count these, 8, 9, 10, 11, 12, 13, 14, 15. Then count these vertical edges here, 16, 17, 18, 19, 20, and count these bottoms, 21, 22, 23, 24. So aren't there 24 edges? Very easy to get lost in those counts. Vertices. Vertices are points at which 2 edges meet. So you're looking for the points. So again, go by levels. On the top level, how many points are there? 1, 2, 3, 4, right? Then go down here, follow the vertical edges to find your next vertices. So here's 4 up here. Down here, I've got 5, 6, 7. Out here I have 8, 9, 10, 11. And down here I have 12, 13, 14, 15, 16. So you have 16 vertices. I will always double count when I do these because it's very easy to miss something. Alright, so here's your one edge. Let's create this left cube here. So I typically will put dots out here. So this edge is 1, 2, 3 units long. So you have to count 3 every time. So from here to get this edge, we're going to go 1, 2, 3. So you want to go in the same space. If you went up this way, these are a longer distance. This way, longer distance. Don't do it. And then I want this top edge, so I've got 1, 2, 3. And then this edge, 1, 2, 3. And then go straight down, 1, 2, 3. And let's go ahead and connect those. So we end up with the front left cube. And then I have to finish this part, so I've got to go down 1, 2, 3. So I need another vertex. Once you get the first cube, it's pretty easy to get all the rest of the cubes. So there's that front left cube, this one right there. So I'm going to draw the front right. So again, 1, 2, 3. Then 1, 2, 3. Then down 1, 2, 3. And over 1, 2, 3. And then I think after this one, 1, 2, 3. So connect those. Takes a little bit of practice for some of you. Some of you, this is like a piece of cake. You didn't even need the isometric dot because you're artistic. I'm not artistic. That would be my twin brother. So all I'm missing is a top cube. So all I need is 1, 2, 3. Nope, that's not good. they go up. 1, 2, 3. 1, 2, 3. 1, 2, 3. Voila. For somebody who's not artistic, the isometric dot paper can really make your drawings look fabulous. But everything was exactly the same length. All right, so if you didn't finish that, just stop where you're at. You can finish it later. I know that'll bother some of you, but we only have 6 minutes left. Am I right? Yeah. So let's flip to the last page. So this is called an orthographic drawing. So definition of an orthographic drawing, how is it different? It's on isometric dot paper, but it does look different, doesn't it? And notice that they say front and right. Technically, well, let's look at it a little bit differently, because that's not typically what I look at for an orthographic drawing, but it should have 3 views, so it shows 3 separate views. You get a top, a front, and a right. I don't know why there's not a left. I personally would need a left too, because sometimes a left will make it a difference, but for our purposes, we'll look at the top, the front, and the right. So underline the correct word to complete the sentence. If you built the figure out of cubes, you would use 7 or 8 cubes. So in this one, we have 1 cube. How many cubes in this column here? 3. How many here? Yeah, 2 here and 2 here. So we've got 2, 4, plus 3 is 7, plus 1 is 8. 8, right? So we would have a total of 8 cubes. But we only see 7. Cross out the drawing below that is not part of the orthographic drawing, then label each as front, right, or top. So for this drawing, if you're looking at it, do I have time to build it? I'm going to build it. So here's my actual building. So this is the top. So from the top, I see 4 cubes only, correct? So notice, and then if this is turned, it would probably be turned this way, right? What about the first one? Would that be the top? It would be. So this is your top. Then for this one, well, let's find the front. The front's a little easier, right? So if I lay this on its back, we'll see the front. For you, I'm going to have to lay it on its back. So this would be the front, correct? So which of these is the front? Yeah, notice that it shows, I can get it over here. It shows hard lines here for when there's a change in levels. And so that's the 4, that's the 2 you see, and that's the 1 popping out front. So this is the front. Then we're looking for the right view. Pop this onto its right side. So this would be the right side. Get it without it falling over. So you see 1, 2, 3, 4 cubes again, right? With 2 changes in levels. So which one would it be? The left one, right? This one? Isn't that your right view? I guess I shouldn't say left. This one is your right view. So this is your right view. So this is actually, what's neither? This is going to be this neither. Anyway, that's neither of the views. That one there. All right, so then the last part, go ahead and fill this in. Is this a net, or is it orthographic, or is it none? This is a net. You would use, and this is one view. What is this? That's the orthographic. That's the proper orthographic. Because this right here is actually the isometric. So this is orthographic, whereas this is isometric. And so this shows you three views. This isometric is done on dot paper. And then this is none. And none. All right, so that is the end of the lecture.